And it's 10 o'clock. Thanks everybody for joining the call here today. I'll give somebody just a few more minutes just to try to get a few people in here, but I will start probably in about 1 minute. We'll talk about the heat treat process simulation with HTP Sim. Okay, that's enough dead air for me. So we'll get started here. Real quick, if you are unfamiliar with the town hall, there is an option under the Q&A to start a discussion. You can post a question here and we will try to get to it at the end of the presentation. I just posted the chat here now so that you guys can see that. So go ahead and ask any questions during the presentation, but we won't get to them until the end when there's time. So today's webinar is based on the heat treatment process modeling with HTP Sim. This is a little bit of a hands-on for us, so we can show the actual software itself, and then talk about a little bit of our modeling capabilities and everything. So here's the outline of today. What we're going to do: we have a little bit of an introduction to Dante, and then a little bit of a heat treatment simulation in general. Then we're going to talk about HTP Sim in general as well. And then we're going to model a really simple example process showing heating and then talking about results at each step. Gas carburization, this one has a two-step process. We're going to talk about oil quenching and then tempering of 4120. Then we'll talk a little bit about advanced applications where we can test quench severity, alloy and chemistry variations in your actual melt, and deep freeze applications, as well as a couple extra. Then finally, we have a carburized gear example. This was low pressure carburized and vacuum, and then high pressure gas quenched. And we have a pretty good example that matches some published work pretty well. And then we do a little bit on the equipment and characterization model. We'll talk about that as we get into it, and then a summary of the presentation. While we're talking, I'd like to have a few key takeaways here. Is the Abacus and ANSYS FEA software require extensive modeling to use, so for your full FEA program. But HTP Sim is very easy to use, and it's a utility that can be used to investigate the variations in chemistry, such as carbon content or alloy composition, and we can also investigate processing times and processing temperatures for your heat treatment process. It can be used to design and optimize heat treatments by reducing furnace time, designing optimum carbon profiles and hardness profiles. So a little bit of background on us. With Dante Solutions, pretty much have everybody here as pictures. Small engineering firm in Cleveland, Ohio. Dante stands for Distortion Analysis for Thermal Engineering, and we were founded in '82 as Deformation Control Technologies, where we focused on modeling thermal process of metals. In the mid-90s, from 92 to 2000, we were part of a large collaborative effort with industry, academia, and the national labs to predict distortion in heat-treated steel alloys. And that's really where the Dante software was kind of born. And since then, we've had sole ownership of the Dante software, and we use it to license the software to users. We use it to develop heat treatment technologies, and then we also use it to consult for projects for customers. So a little bit of a heat treatment process modeling basics. For the most part, you really need to model all sorts of different phenomenon, including phase transformations, multi-phase mechanical models, trip models, mixture laws, tempering, carbon partitioning and carbide, carburization through diffusion and carbide formation, and nitriding. So it's a very wide, broad subject. And for the most part, we have this little triangle here that shows how they interact with each other. So it's not very highly nonlinear. So when you have like heat transfer, you have a temperature-induced transformation. And down here at the bottom, there's a little bit of an animation that shows a little bit of a dialtometry sample animation that shows when you heat a sample, it grows. It gets larger, obviously. And then with steel, it transforms to austenite at a certain point. And once that is complete, you can cool the material down to form diffusive phases or martensite. This example shows a martensite transformation here, and we have a volume growth from that martensite transformation. So when we have the heat transfer, it obviously increases in size, but also when you have phase transformations, you have a temperature, like a volume change due to that phase transformation. And that's really what makes it really complicated for as far as controlling distortion in heat treatment. Today, we're going to be talking more about the heat transfer and the chemical transfer phenomenons using the HTP Sim to model processes. So this is what you get when you get DANTE, the full FEA software. It comes with a bunch of different packages here, including our DANTE library, which is where all the subroutines and models are. It comes with the standard database and then a modifiable user database that you can use to edit your own steels with. But what we're talking about today is it also comes with the utility tools. And one of the utility tools we're going to be using today is the HTP simulator, which you see the little UI window here. We'll get into that here in a little bit. But we also have all sorts of different utilities that are basically little snippets of the full DANTE package. We have several fitting tools that'll help you fit the data to the material database in DANTE. And then there's also a lot of prediction and design tools like G-carb or V-carb. G-carb handles the gas carburization predictions, and then V-carb will handle the vacuum or low pressure carburization models here. We also have several other ones like MAT simulator is like a point-based analysis, whereas HTP simulator is 1D, so we actually get a profile, so we can see hardness profiles and phases as it goes into the depth of a part. So for the DANTE material database, for the most part, heat treatment requires a significant amount of material data. There's a large temperature that we go through, from room temperature all the way up to austenitization temperatures and beyond. So you have to have good data based on those temperatures and carbon content. So for the most part, over the past, say, 30 years or so, we've developed this material database to include pretty much most of the standard materials that you would run into during heat treatment. So there's really no need to develop material data for most users. But if there is, we also have an expandable user database, as I mentioned earlier, where each one of these materials you can modify based on your own chemistry or your own data that you have. So in each one of these folders, there's the phase transformation kinetics, the plasticity mechanical properties, the coefficient thermal expansion and transformational strains. And then there's also hardness related properties that include like your individual phases and your iron carbide coarsenings and things like that for the models inside each one of these folders. You'll notice some of these materials have an XX at the name, like this one we're going to be using today. We're going to use 4120, so this one is 4100 series, and then it would just have 0.2 carbon for the 4120. The XX denotes that it has the carbon ranges for carburization, so it can go all the way up to maybe 0.8, depending on the material, or down to the lowest carbon value for that material range. That includes like 43XX, 48, 51XX, so it's similar properties. I think here's some of the commercial examples that we've used for modeling in the past. Large axle shafts, gears, pretty much every kind of gear that's heat treated, we've run already. So we have extensive experience with those. Geared shafts where it's more of like a hollow shaft here, or even like a hollow tube, like these landing gear that we've worked on. And what I want you to kind of notice when you're looking at these, especially with these images in the middle here, is each one of these can be simplified down into a cylinder or a ring shape, depending on what area you're looking at for heat treatment. And the reason I want you to notice that is because Heat Treatment Process Simulator, HTP Sim, uses the 1D FEA tool. It uses this simplification to where everything can be simplified down into a cylinder or a ring-shaped geometry. And these features includes the heat treatment features like quenching, tempering, and phase transformation and hardness simulation that the full DANTE FEA package has. But it does not have the stress or distortion modeling features because it's really only a 1D simulation. We'd have to have another axis in order to include distortion and stress in our simulations. So what's good, we'll spot this is we can do not only the thermal processes, but we can also do chemical processes. It kind of in the same analysis. That includes gas carburization, flow carburization, or gas nitriding, in addition to all the other thermal processes that we can do. And then here's a little simulation of kind of what the geometry simplification is. It's this is a cylinder here with a given radius, and it's assumed to be infinite on either end. That way we're taking a slice down the middle of the cylinder where we get our data that's not affected by edge effects from heating or quenching or anything like that. It doesn't really need to be infinite. It can be like twice the size or whatever to not have those edge effects. And so HTP Sim applications, these are some ways you can use HTP Sim to modify your processes. You can optimize furnace time for a given part geometry and the selected equipment, so you can reduce or change your processing times based on the data that you get from the results. You can check the effect of quenching equipment or the quenchant or the quench severity on the hardness and phase transformations that you get or phase fractions. You can look at the effect of alloy composition on material grade and hardness, the geometry effect on case depth given a carburization recipe and material. So the gears, they have like a flank that's more of like a convex shape, and then they have the root of the tooth, which is more of a concave, and carbon will diffuse into those regions at different rates based on the geometry. We can define effective tempering times and tempering temperatures for whatever target hardness you want. And then we can also design a deep freeze process to retained austenite, to reduce retained austenite if that's what you were looking for your process, and much more. This is just some of the examples that we have here. So getting into it, this is the process we're going to model today. We're going to assume that we have a 2-inch diameter cylinder made from 4120 material. During the process, we're going to have a furnace heating that up to 925 degrees C. And then we're going to gas carburize at that 925 degrees C with a 0.9 carbon potential for about 4 hours. And then we're going to ramp the temperature down and the carbon content down to 0.8. And then we will oil quench and then have an air cool to bring it back to room temperature. And then we'll temper and then air cool again. And so I am going to do that live with the software. So hopefully everything works well. And so we'll start with there. So this is HTP Sim. As soon as you open it, it's a blank slate, and we have several different tabs here that we use to set up the process, the geometry, and the controls for the simulation. Right now we're on the material tab, so you'll see we'll do our material selection. We will choose 41XX, like we said before, and it's 4120, so we have 0.2 carbon. In addition to the carbon level, you can also define initial conditions of iron carbides, alloy precipitates or alloy carbides, the ratio of carbon in the alloy precipitates, the initial nitriding, if there was nitrogen in there as well, or nitrides. We set the initial phase composition for the material. So for this example, we're using like kind of an anneal condition of 50% ferrite and perlite. You can set your grain size for the grain gross, and you can also modify your alloy composition. So if your melt is a little bit different than what we have tested, you can modify this composition and it'll adjust the hardenability of the material for that. So for the example, like I said, we're using 4120. We're all set for this. We're going to leave all the other options the same, so we can explore those later. For the geometry, we wanted to use a cylinder, so we have a 0 inner radius. And for the outer radius is 25.4 millimeters. And then for the controls, we're going to be using tempering. So I'm going to go ahead and activate this now. This allows the tempering model to be used. Pretty much all of these have different models and subroutines inside the DANTE simulation to account for carbide decomposition. If you have a large carbide, say with like 52100 or something material, you can see the carbides dissolve as the heating in austenite. There's a latent heat model, so you can have this active for heating and cooling. There is alloy carbide precipitation, so when you have high temperature tempering process, you can have alloy carbide growth and precipitation through there. There's the austenite grain growth model, which allows the austenite to grow. Carbon partitioning, it just kind of like has like austenite stabilization during quenching. And then output frequency, this is basically how much results you show when you do your simulation. Right now it's set up to every 10th result. It'll actually display, I'm gonna change this down to 5 because it shows a little more process curves instead of steps. But you can decrease or increase this based on the simulation time. For hardness values, we have HRC or Vickr as an option. Temperature, we have degrees C or Fahrenheit. Time, we have seconds or minutes, and then length, we have millimeters or inches, depending on which units you prefer. And then this is just a nice handy to show you where your DANTE material database is. If you have a different material database, you can reset that to a different place as well. So let's get into the process here. So the last step here is the process tab, and we start with an initial temperature of 20 degrees C. It's at room temperature, and we want to do furnace heating for this. So we would choose a thermal step type. For step type, we can choose thermal, gas carburizing, low pressure carburizing, or gas nitrating, depending on the models that you have. So for this step, it's a furnace heating. We're going to use thermal, and we're going to use it for 7,200 seconds. The rule of thumb basically is 1 hour per inch of thickness. It's a 2-inch cylinder, so the 2 hours should work based on the rule of thumb. The temperature we're going to go up to is 925 degrees. 25 degrees C. And then at the bottom here, the last thing you need for heat treatment simulation would be the heat transfer coefficients. And these heat transfer coefficients can be gathered. I have a couple slides on these later. But for right now, I'm going to use one of our equipments to simply quickly pick the heating furnace here, and then that'll automatically set the heat transfer coefficients for us for that particular equipment. You can characterize any number of equipments with this. So if you have several heating furnaces on your floor, you can adjust this based on each one of those furnaces because they'd be different. I just noticed that changed my temperature, so I'm going to rechange it back to 925 degrees. And then we can just analyze. I'm going to save this into the temp directory. And then we can plot the results. So HTP Sim has several different result plotting. Right now we have temperature over time, but under the settings here, we can also do a single increment. So we can choose the last increment, and then we can plot those results from as a depth of OD, so it's over the cross section of the cylinder. So we can plot that, and we can see that it is all about 925 degrees, give or minus a couple thousandths here. So there's a numerical analysis, so we will get a couple extra zeros here in the analysis. But we did get to temperature. We can see that even at the bottom in the core, we are about 925 degrees. So we can go back to the single point and plot the temperature history over time. And in addition to temperature, we can also do all sorts of variables here. We can do hardness, we could do phase volume fraction. So we're going to go ahead and implement that right now. And you can plot these and you can see the phases. You can see the ferrite and perlite here starts at about 50% each. And then as austenite begins to form, this decomposes to austenite. And you can see this blue line is the austenite transformation. And we can see we get to 100% austenite pretty quickly during the heat up. You can also choose carbon and nitrogen, iron carbides, alloy precipitates, your carbide size and your grain size is different options to display. So that looks good for right now. So the next step that we're going to be using is the gas carburization step. So we would insert a step after the heating. And now that we're already up to temperature, the gas carburization is at 925 degrees. We have a carbon potential, so we're going to change this to gas carburization. And then we have a carbon potential of 0.9. So this is already set up, ready to go for us. And then we could select the equipment as the gas carburization furnace. And that's the only thing we have to change now is the time to go to 4 hours, which is 14,400 seconds. And we can analyze, plot it out. So we can see our temperature got a little longer and the phases didn't change. We're still austenite here. So what we can do is look at the carbon and nitrogen and select total carbon and plot that out. And you can see during the carburization step, we are at 0.2 for the base carbon material. And then as the gas carburization takes effect, we can see that it goes up to about 0.8, which means I forgot to change this to 0.9. Quick, gotta love it. Okay, so now we're at 0.9 proper, and this is the point on the surface. Another thing we can do, since we're doing a single point, we can look at the point in the core. While it's not very spectacular, it does confirm that it is 0.2, the base carbon in the core here. So we can see the difference. I can also show this as the single increment at the end of carburization. We will just choose hardness here as the main, and you can see the carbon profile that was developed based on the first step. Based on that first step, we have a carbon weight of about 0.5. You can select each one of these however whatever you want to look. You have a little bit of window you can look at, and about 0.5 carbon at about 0.6 millimeter depth. So that was step one of the carburization process. We have a step two of the carburization process, which includes a furnace ramp down to 825 degrees. So the first thing we need to do is set the thermal, change that step down to, yeah, that takes 1 hour to get to there. And that temperature is defined by the 825 degrees C. And then we use the same heat transfer coefficients as the heating furnace here. And then I'm going to insert the step after. Now we have our chemical process. I'm going to choose gas carburization. This one's for 2 hours, and it is at 0.8 carbon potential. All right. And then we can go ahead and analyze that step now. And then plot that out. It's carbon and hardness. So we're going to go back to the single point and show it over time. We will look at temperature and the total carbon value. And then from there, we can see we still have our first step. It gets up to about 0.9 potential. We have the temperature ramp down here, and then the carburization at 0.8 for that process. I understand a real process would just change the set points here, but for modeling purposes, we have to do the thermal and then the carburization for the step. So that's looking pretty good. We have about 0.8 carbon at the surface. We can also look at look at the single increment and show the depth from the OD and actually look at the carbon profile that was developed. And you can see the carbon one a little bit deeper here. At that same 0.5 carbon, we have about 0.65 or so carbon depth for that. So now we can safely oil quench this simulation here. So I'm going to add a thermal step afterwards. And again, I'm going to use the oil quench tank that we have developed already for the material. It only takes about 1,000 seconds for that to quench down to the 65-degree oil temperature. And then the heat transfer coefficient is listed down below here based on the part surface temperature. This one is a little more complicated, so it actually really helps with the equipment module that we have here. So I'm going to go ahead and analyze that with that step. You can plot that out. Okay, the settings right now, we have depth from OD. You know what I can do? I can do, instead of temperature, we will choose hardness. So we can see the as quenched hardness at 65 degrees here. When we look from the OD in, you can see the black is the hardness profile, and then the blue is the carbon that was achieved from the process. When I go back to the single point based on temperature, we can look at hardness. If I click hardness, you can see the temperature shows we heat up, ramp down, and then oil quench down to 65 degrees, about 65 degrees here. And then you can see the hardness spikes up at this point to almost 60 HRC. It's about 58.9, so 59 HRC. And the reason for that is if we choose the volume fraction, all phases here. We can see the story again with the austenite formation and the austenite throughout carburization. And then during the quench, I will zoom in. You can see that martensite is being formed when the austenite is decomposing here. We can see we end up after quench with about almost 70% martensite, a little bit of tempered martensite at the surface point, and then some retained austenite because it's still a relatively high temperature, about 13% retained austenite here. Another thing, like I said, we can do the single increment, and we can look at the hardness versus phases. And we can plot this. This is kind of interesting. You can see the depth of the martensite that is formed. You can see that the as quenched martensite is dominating the near surface, but there is some tempered martensite here under the surface, and then that spikes down and goes down here. And then the core is mainly tempered martensite and bainites, upper and lower bainites here. This is like since we have tempering on, this is auto tempering, so this martensite transforms relatively early at a higher temperature, and then it quickly auto tempers in this region to go to tempered martensite instead of standard gas quench martensite. All right, so that is the quench process and the post-processing for that. So we need to look at this at room temperature. So I'll insert a step afterwards and bring this down to room temperature. It is a thermal step again, and we will use the air cool equipment that we have here at 20 degrees C. Is that? And plot it out. You can see since we brought back to room temperature here, we can see we have a little more as quenched martensite, a little more transformation there, and the retained austenite has dropped from about 13% to about maybe 10% or so near the surface. And this is because it's continuing down to the room temperature through the martensite transformation. With that, we can start our temper. So now that we're at 20 degrees C, our tempering furnace, we select that, and we're tempering at 20 degrees C, or sorry, 200 degrees C. And that has the HTC already built in for the temper furnace, so we can analyze that. That is complete. We can plot. And we can see after tempering, the case transforms completely to tempered martensite because we're still at the higher temperature here, and we still have the retained austenite here, so it's mainly consisting of tempered martensite. And then the last step here, we will insert a air cool to bring it back to room temperature, where we can kind of look at the results in a meaningful way. And this one will be 3,600 seconds. And then we can just analyze that. And plot it out. So after the tempering, we do see a little bit of as quenched martensite, some form, and then the retained austenite decomposes a little bit because we're going back through the temperature range after tempering, and it's limited to basically the first half a millimeter or so in depth. We can select the austenite and see that we're down to about 4 or 5% of retained austenite and a little bit of martensite here. When we look at the temperature and hardness plots for the whole process, we can see we have our heat up, our carburization, quenched oil temperature, room temperature, and then the tempering, and then back to room temperature. You can see in the hardness is affected by the tempering. We can see a slight reduction in the hardness as it's being tempered. And then as we move back through martensite transformation at the surface, we have a little bit of martensite that's formed, and that's what's bringing the hardness back up for that process. Now that we have the entire process defined, we can go back and look at each step and make sure that we're hitting the temperatures that we need. A good way to do this is for the single point, and we look at the core temperature. So this first point here would be the core temperature, and we can look at to make sure that we're hitting all the temperatures that we need at the end of each step before we start the next one. So we have the austenitization and we have the carburization. We are at 925 for that. And then we ramp down to 825 degrees before the quench. After the quench, we are at 65, 66 degrees in the core. We are at room temperature at the end of the first air cool. The core gets to tempering temperatures with a significant amount of time here for tempering to occur at 200 degrees C, and then we end the process again at 200 degrees. And so that's a good way to check if you're not hitting your temperatures in your core. You can always add a little bit extra time, or you can cut back a little bit on the time depending on how much time at temperature you can have. And so that is the example that we had today for HTP Sim. And then I'll go back to the slides here, and we can talk about advanced processes or advanced features. So like I talked about a minute ago about the heating time, we noticed with that process that we had with the heating that we were up to about 915 degrees at about 3,300 seconds. So this is pretty close to the actual temperature, the design there. So we keep about a half hour at that temperature, and we can reduce the time. Instead of the rule of thumb of 2 hours, we can get it down to about 5,100 seconds, or save about a half hour of heating time in just that based on the rule of thumb. So you can look at each one of your processes, and like I said, you can trim or add the time depending on what you need for your specific part. So we look at quench severity on hardness. So I have one with a low agitation quench, and then one with a high agitation quench. We can quickly do this in HTP Sim with a modification or you have your equipment module set up to have a high agitation or low agitation HTCs, and then you can simply apply those directly and see the differences. At the actual surface, there isn't very much of a difference. It's still about 60 HRC. This is just the way for quenching, it's fast enough to form martensite, and that won't change very much after that. There's a little bit of change at the case depth. So at 50 Rockwell C, there's about 1/10 of a millimeter difference between the two processes here, but really the big difference is really with the core here. The low agitation cools a little slower, and it shows that we have a core hardness of about 32, 33 HRC for the low agitation, and then the high agitation it stays above 35 HRC through down to the core. So you can test the effect of a lower or fastest agitation or quench severity on your hardness. Another example we have is the alloy composition. So your alloy composition, like I said, we can adjust this. This is a simple example that shows the lowest chemistry range and the highest chemistry range of 4120. You can see that here on the side with 18% carbon for the low end, and then 23% carbon for the high end. So the low chem result here is basically using the lowest of all these values, and then the high chem result is using the highest here. We understand that the melts are different, but this kind of shows the range that you could have with your material if you got the low end or the high end. So the big difference here again is in the hardness. We can see the not only the surface hardness, but also through the core. The core was only about 29 HRC in the low chemistry result. And then the high chemistry result has a little bit of fluctuation here, but if you look at the scale, it's still between 41 and 42 HRC. This is just kind of a numerical thing. So that is a very different, like 30 to 40 HRC difference based on the chemistry range here. And the reason for that is these phases. I have the phases plotted as well. And you can see the low chemistry range is mainly upper bainite with a little bit of lower bainite. And then, excuse me, the high chemistry range is mainly martensite and lower bainite. So the difference in phases there has a significant difference on hardness. So for carburization, the inner and outer radius, we have a little bit of a geometry effect on the carburization depth. I mentioned earlier that the root will have lower diffusion to carbon through it because it has a larger volume of area for it to go into based on the surface. And so we can quickly, a little example here was it made this a ring-shaped geometry instead of a cylinder. Still has the same outer diameter, same process as what we described earlier. But the inner radius is now only 3 millimeters. So it shows like a very tight concave surface here. And the difference between this is slight, but it is a noticeable difference, and especially with longer carburization times. We only did it for 6 hours total here. But for longer carburization or even like LPC boosted fuse schedules, you might have a larger difference of carbon between these 2 points here. But as is about a tenth of a difference in millimeters uh, based on the same carburization profile for both of those radii. For tempering temperature, and we have a core hardness here. So we have two results here. One of them at tempering at 350, and then the one we showed earlier where it was tempered at 200 degrees C. Um, this is for the core hardness, so it doesn't include the carburization. We're just showing the base of it. It's a heat up, and then oil quench, and then air cool, and then temper. In the higher temperature tempering, we can see that the hardness is reduced um, from about 36 to about 33 HRC, so about 3 points of HRC difference based on this hour or so of tempering at 350 degrees. You can adjust not only the temperature, but you can also adjust the time to see the differences in tempering. For the 200C, this is the same kind of thing that we got earlier, where we stayed roughly at 36, 35, 36 HRC. There's a little bit of softening, but it isn't quite as severe as the higher temperature tempering. So you can look at tempering effects to make sure you're achieving your core hardness. And finally, we can also apply deep freeze. Let's say you really have a high requirement for retained austenite to be low. So, and especially for higher alloy steels, this is important as the MF is often below room temperature. So doing a deep freeze process can reduce the amount of retained austenite that's left. You can see with the blue plot here, with including deep freeze, that after bringing to room temperature, we have a little bit more of a decomposition of austenite during the deep freeze, and this brings the martensite to completion. And then we continue with the tempering, and there's a little bit of difference at tempering, but most of it is from the deep freeze here. Like I said, this example is only 4120 carburized here, so the difference here is only about 2%, but it could be significant for your process. So it's always good to look at. Lastly, I talked a little bit about the equipment feature. And so you can characterize your own specific equipment with this module, and then it really helps with defining the heat transfer coefficients. So we do have some generic ones in there. These are the ABC ones I've been using for our example. And these will get you pretty close, but each equipment will be different. So it's good to characterize them, and then you can apply them easily. Again, make it easier to use. That equipment module also stores the thermal and carbon model boundary conditions as well. So it's really nice. And they're just basically text.exe files right now. And then you can have them directly in your DANTE directory. The question is how do you characterize that equipment? A lot of times we really like to use thermocouple probes, where we can use quench probes here on the left. They run through the same heat treatment as the actual parts, and they really help. You can characterize not only the furnace and the positioning in the furnace, but it also can help understand what's going on with the part at that point. You can also thermocouple actual parts. You can go from these little tiny gears here to large landing gears. And those thermocouple data will be really useful for understanding the heat transfer coefficients in your quenching environment. Another thing you can do is use CFD to analyze the problem and get heat transfer coefficients through there as well. We've done a little bit of work with companies who've done this, and they've been pretty successful with that as well. And then we also have an example here. This is some results that worked pretty well. We found this paper from Poland here. You can see the credits here at the bottom. But they had this pancake gear that they ran through a low pressure carburization process. You can see that process here. It's a heat up and then to austenitize, and then a little bit of ramp up to the low pressure carburization temperature. This uses a 3-step boost and diffuse process that was well defined in the paper, so that's why we used it. And then there's a slight ramp down before quenching, and the quenching is a high pressure gas quench for this application. And I understand that this is not an infinite cylinder. This is a pancake gear. This is really thin, but the diameter here is about 20 millimeters, and we're only looking at about the first millimeter or so in depth for the actual carbon case and for the hardness profile. We do expect the simplification from HTP Sim to under predict the hardness in the core here because it doesn't include the heat transfer from like the top and bottom here surfaces. But for what we're looking at, again, carbon case and the hardness is really great for it for this application. So after the processes, it matched really well here. This is you can see the carbon profile is this orange line here that's predicted by HTP Sim, and then each one of these dots, the gray and yellow, are the actual experimental data for that carbon profile. And then for the hardness profile, we have the same thing where the blue and green dots, and then this black line is the DANTE result here. Very, very, very close to the result there. You can see we are starting to diverge a little bit as we get closer to the base material. Again, that is from the difference in the simplification of the model. And finally, we have HTP Sim. It's easy to use. You can simplify the part section, you can apply equipments, and you can do a full heat treatment process in the time it takes to do a webinar. HTP Sim uses the same material models as the DANTE FEA package, so everything's well validated with that. You can use it to investigate processes or material variations. It can be used to design or optimize heat treatment processes. And then it can be quickly simulate the carbon, temperature, hardness, and phase profiles for a given heat treatment process. And that is the presentation for today. So I'll take any questions if you guys had any. Go ahead and put them into the chat. Let me know how I was doing on time. Not bad. A little fast. New post. Can these slides be shared? Yes, they can, Michael. I will send those over. Prepared for that. And so at the end of the slides, just so you know, when I do send these out, a lot of the stuff that I just spoke about was included in these slides here. So at the end of the presentation, you can look through these. It talks basically about the material modules and the features that I've already spoken about, but in an easier to read manner. Right. New post. Yeah. Thank you. Great presentation. Thank you, Michael. Appreciate it. And if there are any other questions, you can always contact us at support@Dante Solutions or go to our website. We have a lot of publications and case studies on the website that you can view. Pretty sure if you have a heat treatment related question, we've probably modeled it in the past. You can find it in our publications. Looks like we have one more response here. How do you add new materials? That's a good one. So the materials, you have our standard database. I can go back up to that. And then you can just request from us and we can give you the user database version of that material. And then from there, you can go and adjust the individual files depending on what you would like to change. Let's say if your melt was a little bit different or something similar to that. Like these are pretty well validated, but some of our customers have different chemistries that behave a little bit differently, and then we've helped develop those materials for them. Good question. For the most part, we ask that people don't modify the standard database files, and then so when they do modify that stuff for troubleshooting, we can always go back to the standard database. Okay, I think that's it. Again, if you have any other questions, don't hesitate to call us or send us an email. We love to talk heat treatment. And then until next time, we'll see you then. Take care.